Do they see now? Okay. Okay. Thank you. What I'm saying is that even though I've presented this non-ideal case that has an input resistance, output resistance, and a voltage dependent voltage source, where in a non-ideal case, if you have this op amp in a circuit, in a quite a complex circuit, you will take it off and then you will put its equivalent circuit and start analyzing the circuit in that sense. We're not going to do that. We will limit our analysis or our discussion to the ideal op amp. Okay? So we will limit our discussion to the ideal op amp. Can I move on? Okay. Now let's see. What's an ideal operation amplifier is, and how does this affect the analysis? Because that's what I care about. I'm caring about doing circuit analysis in here. So we just say that there are three rules that governs ideal op amps. And these are, the first rule is that an ideal op amp have an infinite open loop gain, which means I will assume that the gain of the voltage dependent voltage source is very, very big, infinity. Okay. The second rule is that an ideal op amp have an infinite input resistance, which means that our input is also almost equal to infinity. It's almost open circuit. The third rule for operation amplifier is that you have a zero output resistance. That's to say that the R output is almost zero. What effect does these rules have on the op amp, and how am I going to handle the presence of op amps in our circuits? That's what I really care about. So these three rules will affect how I look at the op amp in an electric circuits, and that's what I really care about. Okay. The whole point is the following. If we have an op amp that I'm considering ideal, that's the inverting terminal of the op amps. That's the non-inverting, the one with the plus is the non-inverting terminal. And here is my V output. So I have a V output. I will have an input, let's call it V1, on the inverting end. Let me have another volt called V2 on the non-inverting end, and I have my V out. We always know that the voltage for me to, I have to refer it to something. So let's refer this to a reference node that is set to ground somewhere in my circuit. Okay. The implication that I have with these three rules are the following. because I have an infinite input resistance between the negative and the positive, I will have no current flowing in. So the current flowing in here is equal to 0. The current getting in here is equal. So there are no current flowing inside to the operation amplifier. And now, if my V2 is given here, so V2 will be plus and minus. So that's my V2. My V1 is plus and minus, and that's my V1. The other implication would be that my V1 and V2 would be of equal voltages. So they will be equal. An ideal op amp input currents, I say that I1, which is the current flowing inside the negative terminal, is equal to 0, and I2 is equal to 0, and that's the implication of the our input being equal to infinity, because our input is equal to infinity. The second thing is that V1, for an ideal op amp, that V1 will be equal to V2. Okay. So V1 is equal to V2. Now also, of course, my V plus will be a positive in here, negative in here, and that's my V output. Okay. All what you really need to know are these implications of the ideal op amp nature that we are dealing with. So let's now consider circuits that has this extra element that's called an operation amplifier. Okay, and see how we are going to analyze it, which means that we need to find the voltage, the currents in different branches in this circuit. But now, in addition to the current sources, the voltage sources, the independent dependent current and voltage sources, the resistance, we will also have this triangle that's called an operation amplifier. Okay, that has pretty much very good power when it comes to doing analog computation. You will see that in the lab as well. But let's see. Let's consider this circuit in here. And you are asked for this circuit to obtain the output voltage V naught. So this, well, would have been an easy circuit without this. I have like a current source, a resistance, and I want to find the voltage somewhere in this circuit. But with this guy over here, now I need just to consider how to kind of like take my eyes away from it and just like put what it is via the rules of it. Which means that if I look at this circuit and I want to analyze it and find the V output, okay, I should again apply the golden rules of the operation of the ideal operation amplifier in the following case as follows. What do I have to say is the following. The rule states the following. Nothing goes inside. So the current flowing inside here are 0. So nothing goes inside here. Okay. There are no current flowing in. That's one. What's the second thing that I should consider is, if I have a voltage here, okay, and let me call it, for example, here V2 at this node, at the non-inverting, so the non-inverting voltage is going to be equal to the voltage in here. So if I call this V1, then the implication of my work is that V1 should be equal to V2. Okay? Now, with this in mind, let's see if we can again like try and solve this and relate the V output to these inputs and analyze the circuit. Now, if you really consider what's V2, what's the value of V2? V2 is directly connected to the ground, yes? So V2 is equal to 0, okay? Which, due to the golden rules, implies that V1 will also be equal to 0. So somehow the operation amplifier gives you kind of like quickly the voltages at 2 nodes in my circuit, and then I can start and work from there. So it gives me the voltage at 2 nodes and relates them to each other, and also gives me the current flowing from these nodes being equal to 0 entering into the op amp. Now, if I look at this now, at this, I can actually take off this as if this is not present in here. Okay. So what do I have? If I just like take this and put its effect, which means that V1 is equal to 0, what do I have? Applying KCL at V1, what do we have? So let's apply KCL at node V1. What do we have? So KCL say that the summation of currents that are entering, coming out of the node is equal to 0, yes? Okay. So if I'm going to check in here, what do I have? I have a 1 milliampere getting in, yes? By convention, if we are assuming that coming out is positive, coming in is negative. So if I want to write KCL at node V1, I will have negative 1 milliampere getting in, yes? I have a 0 voltage coming from the V1 into the ampere. So it's plus 0. There is nothing in there. I shouldn't write it, but I'm just like trying to explain more and more. But honestly, I wouldn't even write plus 0. Okay, it makes no sense. And now I will assume that there is like, so there is a current flowing in, 1 milliampere, red, 0 coming out, and then I have a current like this, okay? KCL. So what's this current? This current is coming out. So I'm assuming V1 is of a higher voltage. So it will be plus V1 minus, and that the voltage in here is V output. So minus V output divided by 2 kilo ohm. And that's equal to 0. Do you guys see how we can apply KCL to this non-inverting side of the op amp? That will be like a cornerstone usually in all your analysis, okay? So op amps, they look like nasty, but actually they are very nice. And if once you apply the golden rules on them, you can actually solve, no matter how like complicated the circuit looks like, you can actually go through it very easily. Okay. Now with this, what I'm looking for is V output. Okay. I have all I have is in here is constant. What is V naught? V naught has already been given by the golden rule to be equal to 0. So I just apply 0 in here. If I do that, I will be stating that minus 1 milliampere minus, because this V naught is 0, so minus V output divided by 2 kilo ohm is equal to 0. Flowing through, so minus V output is equal to 1 milliampere multiplied by 2 kilo ohm. Or in other sense, I can say that V output is equal to minus 2 volt. they usually call this type of circuit transimpedance amplifier. And I'll tell you why. So this one, this type of circuit on which you supply a current to the op amp, and then you set one of its terminal to ground via a resistance that is connecting the input to the output. We call this circuit a trans impedance amplifier. And why do we call this transimpedance? Because a current input is changed into a voltage output and we can like consider as if this is the circuit is a current dependent voltage source. What we have is the following. So that's my V output. And V output is minus I input by RF. This is my RF, this is my I input. So in effect, the circuit brings a current in one input branch into a voltage at the other branch, and I have this voltage has its value dependent on the value of the current input and what is my RF across in here. So I've kind of like created via the op amp a voltage, a current dependent voltage source. Okay. So the op amp is the one responsible for creating these. Now, in many cases, you will not be really asked about like the big names of these circuits, but you should be able to analyze them. Okay, you should be able to analyze them. The feedback resistance, because like we call it feedback even RF because it connects the input to the output, so it's called a feedback resistance, RF. Because at times you will be given problems that are not just like numerical in nature. I can give you like problems with these resistance rather than give you like 2 kilo ohm, and I'll just give it like R, R1, R2, and then you will have to solve it or handle it with the variable names rather than just coming up with numbers. Okay. Any problems about looking at this and applying the golden rules where the current coming into the op amps are zeros and the voltage at the inverting and non-inverting are equal, and then you solve KCL. These are the strategy basically to solve any problem that comes with op amps. Okay. Can we move on? Let's see. Let me just like draw a circuit that we call it inverting amplifier. I'll just draw a circuit and then again ask you to analyze it and see what the output is. So let's say that I have an op amp with the inverting side and the non-inverting side. Again, the non-inverting side, I'm connecting it to the ground. The inverting side is connected to a resistance R1 and a voltage V input. And then there is a feedback resistance that is connecting the input to my output side. That's called RF. And my V output is here. And I will just, like, this is the ground, this is ground, this has to be done with ground. In another sense, in circuits, you will sometimes see that all these are connected with each other as a single point. And you are asked to find V output for this. This setting is quite known, and that's called an inverting amplifier. But again, names are not the issue in here. What I really care about, can you give me what is the input-output relationship? How is V output related to V input in this setting? Okay. In order for us to do that, it's an op-amp circuit, an ideal op-amp circuit. I go ahead and I go through the strategy of equating the voltage at the inverting and non-inverting term and indicating that the current flowing into the op-amps are zero, and then I apply KCL and see how I can relate the V output to the V input. Let's do that. When I consider this, I would say that the current in here is zero, so no currents are flowing inside here. There is no current flowing inside here as well. The voltage here at this terminal, if this is V2 and if this is V1, V1 is equal to V2. That's my second rule of engagement in this. And now I can go ahead and apply KCL to this point. So let's do that. What do we have? So let's apply KCL to V1. What do we have? For the sake of like just giving you another way of looking at things, okay? I want to apply KCL. When I apply KCL, I always assume that my V1 is of higher voltage and everything is coming out, yes? What if I introduce this? I say that this is, for example, I1, okay? And in here, I have I2. And I want to apply KCL to V1. What do I have? Yes. Okay, so you want to write the equations without taking into consideration the I1 and I2. Let's do that. Let's do that. Okay. I always assume that the voltage at the node of interest is of higher potential, yes? So the currents are flowing out of it, if possible. Unless I have a current source, in that case, I have to take its sign into consideration. So what I'm saying is the following. Applying KVL, you will have V1. Yes. This I1. But I mean, again, guys, don't like stick with that in a sense. Unless I tell you, like, tell me what I1 is. In that case, you need to, okay, he wants I1 which goes from left to right. If not given to you in that sense, you can have the luxury of working around with the circuit in the way that you like. Okay. So if you want to write the KCL, assuming that the voltage at the node is of a higher potential, then let's work this out. And let's do the same thing after we will solve the same thing again, considering I1 and I2 in the direction that I've put in the circuit in here. So first, let's just do it without picking or without giving consideration to I1 and I2 the way that I wrote them in here. Because basically what you're asked for is to find V nodes. Yeah? Okay. So voltage at V1 is of higher potential. So I will assume that it has current flowing out of it. Okay. So V1 will have a current in this direction, will have a current in that direction, and the current going into, which is a zero. So what I have is V1. How is the current going to flow from this green side, from V1 into V input? It will be what? It will be V1 minus V input divided by the resistance R1. Do we agree on this term? Okay. Plus, I'm assuming that V1 is higher than V naught and it's going to introduce a current in that direction. Okay. So plus V1 minus V output divided by RF. Of course, there is this plus 0 that I don't really care about. And that's equal to 0. Okay? And now, from the ideal op amp, I know that V1 is equal to V2 and V2 is equal to ground, so V1 is actually 0. Yes? So V1 is equal to 0. From this, if I substitute, I will have the following. I will have negative V input over R1, negative V output over RF is equal to 0. Or if I want to relate V output in the left-hand side equal to something in the right-hand side with V input, I will say that V output is equal to RF over R1 multiplied by V input, and I have a negative sign. Do you guys see that? If I take V input over R1 to this side, and then I multiply by RF, I will have that V output is equal to negative RF over R1 multiplied by V input. Okay. Now let me come up with the final from this is that the input output for inverting op amp directly states that the V output is equal to minus RF over R1 multiplied by V input. Okay. That's called the inverting amplifier. So why is it called inverting amplifier? Again, in that setting, because the output is an inverted amplified version of the input. If RF is 10 kilo ohm, R1 is 1 kilo ohm, so my V output is going to be 10 times my input with a inverted sign. So that's why we call it inverting amplifier when it is in this setting. Let me just go through, rather than doing this analysis with the nodal voltage in that sense, let me show you let me do an analysis that has I1 and I2 in it. Okay. Now, if we consider this branch, guys, okay, what can you say about this branch relating I1 to I2? Right? Exactly. If you look at this, because I1 is entering, nothing is going into here, so I have a 0 in here. So all I1 will actually flow on the upper one. So I can say that I1 is equal to I2. That's another analysis, but gets you to the same result. Now, what is I1? if I want to get a current I1, a current is via Ohm's law has to be like the voltage divided by resistance. Yes. Well, the current, the voltage in here and the voltage in the are the voltage difference across the R1. Yes. So I can say that I1 is equal to V input minus V1 divided by R1. Do we agree on this? Okay. And now that's equal to I2. What is I2? What is this current that goes from V1 into V output? Again, I have a resistance called RF. Across it, I have a potential difference. And now, again, via Ohm's law, I can get I2 to be equal to V1 minus V output divided by RF. Do we also agree on this term? Okay. And now, I know that V1 is equal to V2 is equal to 0. That's again op amp ideal rule. Of course, being equal to 0, it's not necessarily. This is the golden rule. It's V1 equal to V2. But in this circuit, V2 happened to be equal to 0. So now it becomes equal to 0 as well. Now, if we substitute this back in here, I just get rid of V1 because it's 0. So I have V input over R1 equal to minus V output over RF. And yet again, I can say from that V output is equal to negative RF over R input multiplied by V input. Okay. So what I'm saying is like the what you can take out from this is that you have the freedom of moving around with things as long as you are consistent, and you should be able by now to kind of like know what you're doing and like work it out with the way that you want. Do I have this? I mean, kind of like you're in that situation or still not? Okay. Anyway, so anyone still wants this? It's the same thing. It's just like it introduces I1 and I2 in this circuit rather than working it with the nodal analysis. Okay? Okay. Again, don't care about like the really naming and everything. What you really care about is, given a circuit that has op amps in it, you should analyze it. Okay? Maybe in future courses you'll be doing design, so you'll use these. And okay, so I want to amplify a voltage, so then I'll use an op amp, have an RF of the size that you want, so that you amplify it with a amount that you like. But for this course, we're just doing analysis. We're not doing design with circuits. So knowing how to analyze is your cornerstone with what's coming in. So let's look at this. This is another circuit. And in this circuit, you are asked to calculate V output. And I will give you like 5 minutes so that you apply the golden rules and try to solve this problem following the strategy that I just told you about. So take your time now and go ahead and try to solve this problem. And I will be like moving around and checking on you guys, okay? So take out a white piece of paper and jot down something related to this circuit, okay? I'm assuming the same thing from the guys who are like on the streaming of this course. You should be trying to solve this example right now, okay? And then you have like 5 minutes to do that. The strategy is apply the golden rules. The voltage at the inverting, non-inverting are equal, and the current getting into the op amps are zeros, and then go ahead and apply KCL, okay? And I'll be checking on you. voltage sign is when x comes in. If that's the case, that's how we want to do it. Then we say that this is coming into this kind of positive sign. Now it's coming from this is coming out. It would be a minus. So you will have just by these two signs of this.
Yeah. Okay.
Okay. So then why don't you have one conventional state limits?
Yeah, absolutely.
So I want you to check this. Depending on the sign that you have, but you're doing what I want to do. I'm talking about the numbers that you guys. So what I've seen so far is that you guys are following the things, but the numbers are not. I mean, the numbers are kind of like different from one to the other. So probably either we have like a sign that is not prime in one of these. So B1 minus 3 divided by 4 plus B1 minus B2 divided by 10. So you solving KCL original for B1. So it has 3 branches. We already solved for 2. What is the third branch? Which is going to be your third branch. and that's equal to 0. Now, this is an equation that relates V1 to the output.
Yeah.
The output. What's V1? Now, we can relate V1 to no, I mean, this is an equation with two unknowns. I don't want that. I want to find either V1 if I can find a value for it. I just need to find one equation with no forward to find it. Okay, so what's V2? What's the voltage?
It's 0.
The voltage.
Oh.
The voltage is 1. So V2 is equal to 1. Sorry? The direction of? Yes, of course. If the voltage was reversed, then it would have been -1. You have like V2 is equal to 1. Okay. And now by the golden rule, I know that V2 and V1 are equal. So I know that V1 now is 1 volt. And now substitute that in here so you can solve for the out. Okay, so you want to follow this?
Yes.
So what and then usually V1 and V2, you don't have a set aside for the okay. V plus, also okay, and V plus and V minus, okay. It's acceptable, but so you want to the fact that this is one branch. So you know what happened, and then it's kind of like focusing on each other. And then we yesterday or the day before, and then we have like a very serious yeah, but you kind of like, and I don't know if it was you or not, 4 plus 5 plus 3, 4 plus 5 plus 3, that's equal to 12. But what you have is that you just went with 4 plus 5, and you drop the 3 and then add 9. I don't know, I'm not sure if it was you or someone else. That's like, focus. Okay? Focus. Okay. Okay, so back to this. Like most of you are on the right track, but I've seen also that there are some of you who make silly mistakes when it comes to like plugging the numbers and working with the actual values. Okay, so if it's up to us to work this, again, the golden rule states that the voltage in here is equal to the voltage in there. This voltage is 1 volt, so I know that the voltage here is 1 volt. I can work with that. Okay. Or, so knowing that the voltage here is 1 volt, I can write and say that current flowing in, and I have a current flowing out. So I can say that 3 minus 1 divided by 4 kilo ohm is equal to, and now I'm not doing KCL, I'm just doing that this branch and this branch just happen to have the same current flowing in them. So 3 minus 1 divided by 4K is equal to, the current flowing out from here is due to the fact that I have a voltage of 1 volt that I'm assuming is greater than V naught. So it's like 1 minus V naught or V output divided by the 10K. Okay? Am I missing something? What? What?
Why is 3 volt not minus 3?
3 minus 3?
No, like, why is 3 volt? Like,
They switch the sides.
Yeah. Why is it 3 volt? Because it's 3 volt in here and it's positive on the top side.
like the current is going,
This way.
yeah,
Okay. So the 3 is bigger than the 1, definitely.
will it be minus 3?
It's minus 3? Where do you get the minus 3 from?
Like, because the current is going, like, clockwise direction?
Okay, there is no current flowing clockwise or anti-clockwise. I'm the one who looked at this and said, I know that this is 1 volt, yes? Do you agree on that? Because of this, I'm saying that 3 is definitely bigger than 1, so the current will flow in the direction that I've thrown in here. I'm not putting any clockwise or anti-clockwise on this. So this comes from the fact that the current flowing in has to flow out. And there is nothing going inside the op amp. That's the equation. Now, if I want to do KCL, and I have certain conventions in my mind that whenever I'm doing KCL, the voltage at the node of interest is higher than anything else, and it will have the current flowing out of it, then I can write, so KCL at V1. So I'm assuming the voltage in here is V1, okay? That's another way of doing it. So I have a voltage V1 here. I would say that V1 minus 3 divided by 4K plus, I'm assuming that V1 is of higher potential than anything else, plus V1 minus V output divided by 10K, so that's the second branch, plus the 0 is equal to 0. Solve this, you will end up to this. It's just a sign difference that is consistent. And I don't know, are you guys following on this or not? You can do that, you can do this. You will end up with the same thing. If I'm doing KCL at V1, then I'm just going with a convention in my mind that V1 is of higher potential than anything else. So all the currents are flowing out. This is the case, except if I have a current source that dictates its direction on me. Something similar to what happened like in here. This current source is coming in. There's nothing for me to do about it. It's coming in. The sign of it is depending on my convention. If my convention is the current should flow out. That's the positive sign. Then this one gets a negative, and that's why I put this with a negative sign in here. Okay? And I was moving around, and one student, fellow student of you guys, said like, okay, no, I want that this to be positive. And I told him, okay, so now your convention is that the current that are coming in are the positive sign. And if that's the case, when you work with that, you would have the 1 milliampere positive and this green one in a negative sign. So you will have this the same thing, but with these signs inverted. We end up always with the same equation, guys. Okay? Someone might not write this way. One would say like, I don't like to say everything equal to 0. I would say that coming in is equal to coming out. Okay? But then again, it's like you have to see, do you have something coming in by dictation of the nature of the problem? Yes, this is coming in. There's no way that you change that. You can, this green, because it's still unknown, you can't say that it's coming in or coming out, by the way. And if you say it's coming out, you would say that V1 is higher than V naught. And then you would have like V1 minus V naught divided by 2K. If you are assuming it's coming in, then you would have it with the same side as the 1 milliampere, and it will be V output minus V1 divided by 2K. And this has to, I mean, this, guys, this is like, it should be like second nature to you, okay? You shouldn't be experiencing trouble or hesitant about like how things are, okay? Again, this will only, you will only acquire this skill by solving lots and lots of problems, and then you will acquire your own sense of working with things. You'd like to have everything in one side equal to 0. No, I would like to have like the coming in equal to coming out. And then after solving, you will come up with your convention that no, it's like coming in is positive for me. If you do that, then you are going to again come up with the same answer, with the same equation, but maybe you'll have it opposite sign than your friend sitting next to you. Okay? But once you solve it, you will find that you end up with the same answer. Okay. Now, if you do this, and if you do the math for this, of course, V1 in here, V1 is equal to 1 volt due to the fact that this is equal to that. Okay. And if you just solve for it, you will have that V output is equal to minus 4V. Okay. So that's my final answer. Okay. Are we okay with that? Mostly. Okay. Now let's see if we can check on this. Okay. Let me just draw another circuit and ask you to analyze it. Okay. And I'll have the circuit with not values, but with variable names. Okay. Let's assume that I have what I call the non-inverting amplifier, which means that my input is on the non-inverting side of the op amp. So that's my op amp. Non-inverting. Now, if you have the V input in here, and then you have R1 and ground, R feedback, and V output, and all this is ground. I want you to get me V output in relation to V input. Go ahead. Let me throw in a couple of nodes, voltages for you so that you can Let's call this V2. Let's call this V1. Okay. And go ahead. Again, I'm giving you a couple of minutes so that you can solve this. What? V output. What's the V output to V input? Same strategy, same path. Again, I'm giving you time to do this on your own.
We're trying to find V naught, right?
Yes. V node, V output. Maybe that's, I want to have V out in relation to V in. So I want to have an equation, V out on one side, V in and bunch of resistance or whatever on the other side. Are we moving along or are we just like wasting the time? Are you trying to solve this? Do you have an idea how to solve, I mean, do you have something in your mind, but you're not capable of actually like putting it on paper? I'll be moving around and checking on you guys.
So that's perfect. Better way of so that's totally right. But then better way of doing it is that the output is equal to and take the input count from these. So it's like the input multiplied by and then that one. Yes, that's just take the input from directly from these two. Okay. That's like first part is good because you want the I one that's right. What do you do? So V1 minus 0 to the power of R1 plus V1 minus V action minus to the power of 0. And you
Did you figure it out? Numbers.
Okay. So you guys have solved, most of you. Let me just do it in here. So I will start saying that V1, or I'm sorry, V2 is equal to VI. Okay, that's my equation 1. From op-amp's rules, ideal op-amp tells me that V1 is equal to V2. That's ideal op-amp equation, okay? Which means that now I know that V1 is equal to V input. That's to say that the voltage in here is known, guys, okay? I know the voltage here. Now, if I want to apply KCL to this node, so apply KCL to V1, I will have the following. I will have V1 minus 0 divided by, should I say minus 0 so that, okay, so that you guys don't lose anything, okay? So V1 minus 0 divided by R1 plus V1 minus V output divided by RF. It should have been plus 0 because the current going in here, but I shouldn't write it. That's equal to 0. Now if we take the V input and V1 and V output in one side, so what I say is the following. I will have V input divided by R1 plus V input divided by RF is equal to, and I'll take this term to the other side, V output divided by RF. Let's multiply all by RF, and let's take V input common factor from here. So I will have that V output is equal to V input multiplied by RF divided by R1 plus 1, and that's what I have. Most of you got that in different, I mean, you have it, but probably didn't like bring it out to the final nice form. So V output, the input output relationship for the non-inverting states that V output is equal to 1 plus RF divided by R1 or I input, okay, multiplied by V input. Okay. So the output is the input multiplied by this factor, and it's with the positive because the input is at the positive term of the op amp. Bear in mind that when we had the inverting, remember that was the inverting. Okay. The output was the input multiplied by a factor, which was RF divided by R1, and I have a negative sign because the input was at the negative side. Okay. You only really care about this if you're doing analysis, if you're doing, design, that you can bring these together to make something out of a V output of your preference. But for us, we're just doing analysis. And I will just finish this lecture by this. And again, I ask you guys to do it. So this lecture, I'm not doing anything. You guys are doing all the work. Now, I want you to be like really quick about that, okay? Just like go with your guts about how to move along with this circuit to find V output. I'll give you 1 minute because I only have like 2 minutes left probably. Like think about it before committing yourself to writing anything down. If I look at this and I apply the golden rules, a couple of things just come up to my mind and I can go from there. What's the final answer? Is 2.31 volt. And that's a nice smile. Okay. And now I have, no, you guys are gonna stick with me until I finish it, okay? Anyway, so I'll do it 2 ways, okay? I'll do it like 2 ways. If I look at this, and just like I'm kind of like into this and I understand how things works and everything. I know that the voltage in here is 3.7 volt, yes? That's the same voltage in here. This is a short circuit, so that all these points are 1 point, which means that from this I can take, I know the voltage in here. The voltage at this point is 3.7 volt. just flowing through the circuit, okay? And now I know that across this branch, I have a 3.7 volt. And I want to have V output. This branch has 12K and 20K in series. So I can apply voltage division. So via voltage division, V output is the 3.7 volt multiplied by the 20K divided by 20K plus 12K. That's the quick way of going through this, okay? And that should be, it gets you that V output is equal to 2.31 volt, okay? Let's do something else, okay? Let's work on here and apply KCL at this node. Okay? So for this node, I have Vx in here. Okay? So let's apply KCL at Vx, at this node in over here. What do we have? Yes, I can say that the current flowing in here is Vx minus V naught divided by 12K. Yes. That's equal to what? Yes. That's you see, like in here, that's 0. Yes. So I have something wrong in here, by the way. I have the current in here. Well, I still need to find what's the current in there, and that I don't know by any golden rules. Yes, so I'm kind of stuck in here. Okay, because like I don't I know the current in here. Yes, that's Vx minus V naught divided by 12. The current in here is 0, but what's the current in this, like the head of the triangle? I don't know. Okay. So then this would not be a way of going with that. I cannot really handle this, okay, from that side. But I can state that Vx is equal to 3.7 volt. Do we see that? Yes? We see that Vx is 3.7? And again, if I know that Vx is 3.7, I can say that the current in here is the current in there, and I can relate Vx to V naught. Okay. Okay, guys. So I'll stop in here, and thank you for attending, and I'm sorry for taking it over time. We'll continue on next Tuesday. Okay. Problem set. Now you can start working on problem set 5 even, okay? And then if you have any question, you can bring it on next time. Thank you very much, and see you. Enjoy the weekend. See you on Tuesday.